Hi, this is video 169 and it's the video that many of you have been waiting for. We're finally to the topic of asset and liability matching and immunization. The first of a bunch of videos on that, I hope. It was by God's grace that I made it here today in Minnesota here on January 29th, 2019. As you can see from my phone here, it's very, very cold today, -9 degrees Fahrenheit. Wind chills like -30, -40, and then tonight it's going to get down to an actual air temperature of about -30 degrees Fahrenheit, about -35 degrees Celsius. You can see further on here if you look at Wednesday there, -29. Wow, really, really cold. This is record cold even for Minnesota. So hopefully I'll make it back safely here. But let's get onto the problem here. It's an October 2018 SOA Sample Exam problem, number 73. And this is quite a mouthful here. Actually, the problem statement looks easier, but the description is kind of a mouthful. Assuming a portfolio of assets and liabilities has been Redington immunized, we've never said what that means, at a certain interest rate, we want to find the ratio of two asset values that are paid at two different times in order to match, though not exactly match, a liability value at yet another time. So here we see the problem. Trevor has assets, cash effectively, at two different times, time 2 and time 9, values A and B. And then he's got a liability of $95,000 at time 5. Okay, now this is a person who's got this portfolio of assets and liabilities. In insurance context, you'd have an insurance company having a portfolio of assets and liabilities. And the motivation would be, your liabilities, for example, would be claim payments, and you want to have enough assets, enough cash, effectively, to be able to make those claim payments and also make money as well, including in situations where interest rates change. That's the overall big picture. But we are talking about Trevor here. Trevor has achieved Redington immunization in his portfolio using an annual effective interest rate of 4%. We want to calculate the ratio, A over B, the ratio of these monetary values, A and B, that are paid at times 2 and time 9. So the statement of the problem is not real long, but there's a lot in the background that's going on here in understanding what to do. So this is a kind of complicated thing here, a complicated and long video that we need to do here to understand what's going on and solve the problem. And the calculations are going to be kind of messy. So part of the difficulty is just understanding the concept, and part of the difficulty is the calculations. So hopefully I can get those things across and get you both the main idea and the details right, and I don't make a mistake, hopefully. So here's a time diagram, a timeline showing where the payments are made, and we're going to think about present values here. I guess I'm going to put the assets above the liabilities here, above the diagram. We've got assets payments of A and B at times 2 and 9, A and B there, and then a liability of $95,000. I'll just write a 95 here at time 5, so these monetary amounts would be in thousands. What does it mean to achieve Redington immunization at the given interest rate? Here's the intuition, and then we have to get into lots of details. Intuitively, there's three things that are really going on. You want to match up the present values of the cash flows for both the assets and the liabilities. That's one thing, match up the present values at that interest rate. Secondly, you also want to match up the rate of change of those present values with respect to the interest rates, the derivatives, when I is 0.04. That effectively matches up the durations, if you think about it, both Macaulay and modified. And the third thing you want is you want to think actually about second derivatives. You want the second derivative for the assets to be actually bigger than the second derivative for the present values of the liabilities. Because what that's going to do is allow the net asset minus liability present value to be a function that is concave up near I equals 0.04 in this case, which basically means if interest rates change a little bit, get a little bit higher than 0.04 or a little lower than 0.04, your relative standing, your position, will be to a surplus. that'll be your present value of the assets minus the liabilities will be positive. So that's a good thing. Okay, that's the big picture, but now we need to get into the nitty-gritty details. So let me write down two functions. P sub A is going to represent the present value of the assets. This A means assets. It's not the same as this number A, which represents a particular cash flow that is an asset. So the present value of the assets relative to an arbitrary interest rate, I, we need to take A and B and bring them back to time 0. So we take A times 1 plus I to the negative 2 power, and add on B times 1 plus I to the negative 9 power. And then we'd have a similar function, P sub L of I, L representing liabilities. Take the liability payment, just one of them, there could be more, but in this case there's just one, and bring that back to time 0, 95 in thousands, 95,000 times 1 plus I to the negative 5. Okay, so those are going to be the functions representing the present values. These are going to be equal at 0.04 when I is 0.04. We also want, again, the derivatives to match up at I equals 0.04. So let's go ahead and take the derivatives as the next step. Using the power rule, bring this negative 2 down in front. You'd also have to technically use the chain rule. The derivative of 1 plus I would need to be multiplied, but that is just 1, so we don't actually have to write that down. So we bring the negative 2 down in front, get negative 2a, 1 plus I, subtract 1 from that exponent to get a negative 3, and then bring the negative 9 down to get a minus 9b, 1 plus I to the negative 10, again times 1 in each case, but that doesn't affect things, so we don't bother writing it down. And the derivative of the present value of the liabilities, bring down the negative 5 times 95 is negative 475 times 1 plus I to the negative 6. And again, you do want the second derivatives to be calculated as well, and you want the second derivative of this one at 0.04 to be bigger than the second derivative of this one at 0.04. That condition is necessary for Redington immunization. It's not necessary for solving the problem, actually. These first two conditions being equal, these equalities at 0.04 being equal, are enough to calculate A over B. Let's calculate the second derivatives right away anyway. And at the end I will remark and maybe even do a calculation, although it's going to make the video longer, to confirm that the second derivative for this one's bigger than the other one. Bring down the negative 3, you get positive 6a, 1 plus I to the negative 4. Bring down the negative 10, get positive 90b, 1 plus I to the negative 11. To calculate the second derivative of this one, negative 475 times 6. Negative 6 would be positive 2,850, 2850, 1 plus I to the negative 7. Okay. But again, we're just going to use the first two here to ultimately solve for the unknowns A and B, where this A again represents a monetary amount, where this A represents the word asset. So what do we get when we plug in I equals 0.04? PA of 0.04. We're going to get, let's see, put in 1.04, that's 1 plus I. Its reciprocal is V, present value discount factor. Same as 1 plus I to the negative 1. Here I need to raise it to the positive 2 power because it's 1 over 1 plus I. Positive 2 power, square it. The coefficient of A is going to be 0.924, 55621. And then the coefficient of B I get by raising V right there to the positive 9th power. That's 0.702586. 0.70258674 times B. We want that to equal, set this equal to PL of 0.04, which is going to be a specific number. Again, V is there. Got to raise that to the positive 5 power times 95, and this is 78.5 0.083075514. I hope you can see we're going to get a system of two linear equations and the two unknowns a and b. And it's not real pleasant coefficients, so this is a bit of a pain. I will show you, how you can solve it as quickly as possible with calculator help. It's not the most exciting thing, but I hope you hang with me for that. Now I plug in 0.04 into the derivatives. Okay, looking at this one, I've got v to the positive 3 power, there it is, times negative 2. I didn't put the negative sign in there, so I get negative 1.77799272a. I'm going to get a minus, okay, plug in v again, raised to the positive 10th power, times negative 9, I'll just do times 9, and then I've got the negative sign here, so I get negative 6.080077752. I'm also looking at my answer key, so I'm trying to avoid mistakes here. Set that equal to PL prime of 0.04, v to the positive 6 power times negative 475. It's going to be negative 375.39939997. Check my answer key. That looks good. Okay. All right. Now we're going to solve this system of linear equations for a and b. You could do it by substitution or elimination. With such messy coefficients, I think the inclination is to maybe use substitution, but here I'm going to do it by elimination and show you can do it that way. Let's do it this way. Let's eliminate the b. And how can we do this? Listen carefully. So I can ask myself, what do I need to multiply this by to make it equal to positive 6.080077752 so that when I add those two equations, the b's will cancel? Well, take 6.080077752 and divide by 0.702586674. Whoops. Sometimes my calculator does that and I don't know why. To divide by 0.702586674. Positive 8.65. That's going to be my multiplier of the first equation before I add it to the second equation. So I'm going to maybe put a little note over here, times, maybe I'll store this number as well, 8.6538461. I'm going to store this in register 9. Store 9 is what I just did. So when I multiply that times the b term, I'll get a positive 6.08b, and I can add it to this and the b's will cancel. I've got to multiply it times this and also that as well before I add. Times 0.924555621 gives this. Add it to this means I need to do a subtraction. I get this minus 1.77799272. The a term looks to be 6.222974443a. Again, there's no b term because those canceled. I got to multiply the 8.65, again, recall 9, by the 78 here. So I'm trying to show you how to solve this by elimination as quickly as possible while talking at the same time. I get 675.7189 after multiplication, but now I need to add it to negative 375, which means I need to subtract subtract 375 minus 375.39939997 gives 300.3195156. Look at my answer key. I think that looks good. Now solve for a by dividing both sides by this. Divide by 6.222974443. A is about 48.25980228. What A is. And now find B. I can use either one of these equations. Let's use the first one. Maybe I'll store the value of, let's see, do I need to store the value of A? Maybe what I'll do is I'll multiply A. I'm going to plug it in up there. So I'll multiply it by 0.924555621, and I'll store that maybe in register 8 times 0.924555621. Store that in register 8. Well, I probably didn't need to do that because I'm going to subtract it from both sides. Negative and then plus 78.083075514 is that. I didn't need to store. Now divide by this coefficient of B. Divide by 0.70258674. Is that the right answer for B? Yes, it is. B is 47.62995562. So the ratio A over B, I'll take the reciprocal of B to get that and multiply times A times 48.2598028 is about 1.0132, and that is the correct answer. That is answer D on the sample exam. So that's the answer to the problem. But did this really achieve Redington immunization? This is actually not enough to verify that it definitely has achieved Redington immunization, because we need, again, the second derivative condition to hold. We need the second derivative of this to be at 0.04 to be bigger than the second derivative of this at 0.04. Let's check that. And then I'm going to draw a graph to think about the meaning of all this. So the second derivative at 0.04, I'm plugging 0.04 into this thing here, and then I'm going to also plug it into this thing right now. So, continuing the calculations, again I've got V, 1 over 1 plus I, right there. I need to raise that to the positive 4th power, multiply by 6, and then times A, which I know to be 48.2598. Let's see, did I store that in register 9? No, I didn't. Okay, I didn't store A. Okay, let's just go ahead and multiply by it. Times 48.259. That's why it would have been good to store A. 0.228. So this is about 247. I'll just round to the nearest cent, so to speak. 247.52. Then I need to add this one. There's V, raise it to the positive 11th power, times 90, times B, 47.629955562, gives a large number, 2,784.56. Add these, you get a second derivative in value. Oops, I did the wrong thing there. I think, did I multiply or something? 274.56 plus 247.52, 3,032.08. The second derivative of the liability function at 0.04 is indeed smaller. Looking up here, here's V, raise it to the 7th power, times 2850. You do get indeed a smaller number, 2165.77. That's verifying the second derivative of the asset function at 0.04 is bigger than the second derivative of the liability function at 0.04, and so that means we have achieved what's called the Redington immunization, which again is different than another kind of immunization called full immunization, though they are related. Let's end the video by just thinking about what this means in terms of the graph of a function that Broverman's book calls h of I. H of I is the difference, present value of the asset income stream minus the present value of the liability income stream. It's that difference, and therefore the derivatives of H are also differences. Like this, by linearity of differentiation. And then if you plug in 0.04, into these equations and use what we've found here based on the values of A and B that we found to solve the problem. We can say h of 0.04 is 0 because we made these two things equal to each other. And h prime of 0.04 is equal to 0 because we made these two things equal to each other. And h double prime of 0.04 is positive because of this condition right there. What does that mean? It means something very important about the graph of h as a function of I. You know from calculus that, well, this being true means the function has an intercept at 0.04. That's where it crossed the I-axis. This being 0 means the slope there is 0. So you might have a local max or a local min, or neither. It could be an inflection point as well. When I say the word local, that's also called relative. Local max means relative max. Local min means relative min. But the fact that h double prime of 0.04 is positive, and technically the fact that h double prime is continuous, means the graph is concave up here near 0.04. So in fact, it's got to be a local minimum. It's really the second derivative test here. On some little interval around 0.04, the graph of the function looks like this. You've got a minimum. You've minimized h of I, which means for I values close to 0.04, the present value of the assets will be bigger than the present value of the liabilities, which is good. You're, again, into the surplus position if interest rates change by a little bit. It's not enough to know what happens as you move further away from 0.04. If indeed you do graph this function, we could graph it on a calculator, and you see that the graph is above the I-axis for all positive values of I, then you would call that fully immunized. But the fact that we've done it locally here based on the second derivative being positive and verified that we have a local min to this function, h of I, it means this portfolio is Redington immunized. Thanks for watching.